SwayamPrabha. Digital India. Educated India.
Hello and welcome to lecture 64. We are discussing about the design of industrial fans. In last lecture we were discussing about design of wind tunnel fan. We have discussed different approaches which are being adopted in order to finalize the design of wind tunnel fan. We were discussing about the aerodynamic loading, we were discussing about the structural requirement, we were discussing about different requirements for such kind of fans. And finally we have come up with the strong design for that wind tunnel. Now later on we started discussing about different other applications of industrial fans, and there we were discussing like they are being rated differently compared to what all we have realized up till now in sense of axial flow compressor or axial flow fan. These fans, they are being rated in a different way. As we have discussed, it has been rated in terms of CFM, in terms of pressure rise as inch of water column or meter of water column. Then we realized they are being operating in the different operating configurations where temperature, pressure, altitude, all those terminologies, they are of great importance. So let's take one design for such kind of application. So let's see, we are looking for designing a ventilation fan for paint spray booth with design rated flow rate of 635 CFM. The fan draws the air from the booth which is at atmospheric pressure and temperature of 298 Kelvin, and that's exhaust into open atmosphere. The outer diameter of the fan should not exceed by 0.28 meter. Since there are no outlet guide vanes, the mean exit swirl should not be less than 20 degree for efficient exhaust. Take Cp to be 1005. So my exit swirl that need to be less than 20 degree. So here in this case, this is what is our ventilation fan, and for that ventilation fan we are having data like temperature and pressure, and my exit condition, that's what is atmospheric condition. My volumetric flow rate, that is given in sense of CFM. So just realize this CFM is nothing but it determines the amount of air that the fan can move through the room while operating at the highest possible speed. For larger speed, highest rating of CFM, that's what is required. That's what will be helping us in sense of efficient cooling of that room. Now here in this case, my tip diameter should not exceed by 0.28 meter. So let's try to explore the design possibilities for this. So here in this case, it says it is not having exit swirl, so my fan will be looking like this. So I will be having only rotor. Now in order to do the design, we need to have certain parameters. Now my casing diameter, that's what is one of the constraint that is given, but nothing it is mentioned in sense of what need to be my pressure rise. My flow rate, that's what is given in CFM. So now the thing is here we need to have different velocity components to be known. Once we know our velocity components, we can calculate our flow angles, we can calculate different velocity components. Then we can check with our parameters like diffusion factor, degree of reaction, de Holler's number, all those, that's what will be common for all kind of axial fans. So that's what we will be taking as a reference. Now once we are doing our calculation at one of the station, here in this case we can say this is what is only rotor, and that too it is a small diameter. This may be in a subsonic region. That's what will be decided based on what pressurized we are expecting. Now here it is a tricky, and we need to understand my exhaust pressure, that is what is say atmospheric pressure. So we can say my pressure rise expected that will not be coming in a large number. That means this fan is a subsonic fan. So we will be doing all our calculation at 50% span. Later on we will be applying our world distribution. We will be going with say free vortex kind of design in order to simplify the design methodology, and we will come up with what all will be the dimensions, what all will be the angles, and how my blade will be looking like. So this is what all we will be doing in this lecture. Now here in this case, nothing it is been mentioned in sense of velocities. So what we will be doing, we will be assuming certain axial velocity. So let's say we will assume axial velocity to be 10 meter per second. Just realize one thing, this 10 meter per second, that can be 40 or 50 meter per second, but we need to understand we are not handling large mass flow rate, where volumetric flow rate is not that much. So we need to assume smaller numbers. So let's see, we are taking say 10 meter per second, and it says like my exit swirl angle, that's what suppose at this moment for mid station we will be assuming say 15 degree. Now my entry pressure, that's what is say atmospheric pressure, or say it is 101325 Pascal. Now what we know, my exit pressure, exit total pressure, that's what we can represent in sense of my static pressure plus half rho c square. This is what is my exit absolute pressure, what we are discussing about. Now for this case what is given, it says my exit pressure is atmospheric pressure. So we can say my static pressure P2, that's what is equal to P01. They both are same. Okay. So if this is what is your case, then we need to calculate what will be our delta P0. That delta P0, that's what we are representing here in sense of static pressure and absolute velocity term. So here in this case my P0, P2 and P01, they both are same. So we will be writing delta P0 as 1/2 rho c2 square. Now this c2, that is nothing but the absolute velocity with which my flow, that's what is coming out. In this case we have assumed our angle of swirl, or say my absolute flow angle, to be 15 degree. So if we are writing that in terms of say axial velocity, then we can write down my absolute velocity, it is Ca by cos alpha 2. Now if we are putting this number, my delta P0 is coming 65.65 Pascal. You can imagine this is what is a small pressure rise we are expecting. This is what is a different kind of fan, that's what we are designing at this moment. Okay, we have designed for pressure ratio of 1.2, we have designed the compressor for pressure ratio of 2. Now we are talking about small pressure rise of 65 Pascal. Let's see how do we proceed further with. So what is given, the required volumetric flow rate, it is given 635 CFM. Now if we are accounting for some kind of losses, let's say we will be taking design for 20% higher CFM value. So we will be taking our volumetric flow rate as say 1.2 into 635. So we will be designing our fan for 762 CFM. Now the conversion for CFM to meter cube per second, that's what is given. So that's what is giving me my volumetric flow rate to be say 0.36 meter cube per second. If I will be multiplying that with density, that's what will be giving me kg per second. So you can imagine this mass flow rate, that's what is coming on a lower side. Okay. Now this volumetric flow rate we are writing in sense of say area into axial velocity. This area we are representing as a pi r square, and this is what we are writing in sense of hub to tip ratio. Now hub to tip ratio for such kind of configuration, we can say roughly we can assume that to be 0.5. Now here also we need to accommodate our motor in hub region. So sometimes if the dimension for that motor is known to us, so based on that we can decide with our hub diameter. Here it is nothing mentioned in that specific way, so we will be considering this hub to tip ratio as a 0.5, and if we are putting that, it says my hub diameter is coming 0.0625 meter. We are talking about small dimensions. Okay. Now once this hub diameter, that's what is known to us, our next calculation, our next requirement, that's what is to check with our peripheral speed, or we need to have what should be the rotational speed. Now here also we are having number of options, that's what is possible. Maybe if the requirement says, maybe those end user they will say I am having motor that's what is having rotational speed of 3000 rpm. So you can straightway take that as a rpm. Now we have discussed for the design of say wind tunnel fan, we will be having certain amount of slip. So rated speed, that's what will be say 1440 rpm, 2400 rpm, 3000 rpm. So we will not be getting exactly that number, maybe slightly on a lower side. Okay, so one way is you can assume your rotational speed, and based on that we can calculate what need to be our peripheral speed. But here in this case, let's take a different approach. Let's assume CA by U hub, that's what is equal to 0.55. You can take it. Okay, since my axial velocity we have assumed it is 10 and my CA by U value it is 0.55, it says peripheral speed at the hub it is coming 18.18 meter per second. Now based on that we will be checking with the rotational speed. It says this is what is coming say 2777.7 rpm. So roughly we can say this is what is in the range of say 2800 rpm. So now what we have, we are having our hub radius, we are having our tip radius, we can do our calculation for the mean radius, and our peripheral speed, that's what we are taking 2800 rpm. So based on that we are able to calculate what will be the peripheral speed at different locations. Okay. Now once this CA value, peripheral speed value, those numbers are known to us, we are looking for the design of the fan. So we will do our design at the mid station. So similar approach what we have opted earlier we will be going with. It says at mid station we can calculate what will be the total temperature rise, that's what is given in sense of pressure plus delta P0 what we are expecting, and it is in sense of say polytropic efficiency and entry temperature. So here we are assuming our efficiency to be 80%. So if you are taking this as 80%, my delta T0 you can see this is what is coming 0.0689 Kelvin. That's what is a small pressure rise, total pressure rise what we are expecting. Because my pressure rise what we are expecting, that is also low. Okay. So once this is what is known to us, we can calculate, we are comparing our aerodynamic work and thermodynamic work to be same. So we can write down Cp delta T0, that's what is U into Cw2 minus Cw1. Now this Cw1, that's what we are taking that to be say 0, we are assuming our entry to be axial one. So under that configuration we can calculate what will be our whirl component at the exit, and that is what is coming 2.57 meter per second. Now this whirl components one, this is what is known to us. We know our next step, we will be calculating our other parameters, like we are looking for our blade angles. So beta 1, or we can say 10 beta 1, it is given by U by Ca, and that is coming 70.01 degree. Same way my exit flow angle, we can say this is what is coming 68.13 degree. Now this delta beta, that's what we can calculate based on our beta 1 and beta 2. You have to be very careful whenever you are doing your calculation at mid station. Do not forget to plot velocity triangle. That's what will give you idea and understanding. Now this is what it says, my delta beta is coming 1.88. You can imagine my deflection angle, that is also coming to be lower. This is what is a different kind of design. Okay. Now once this is what is known to us, our whirl angle, it says that should not be more than 20 degree. So let's calculate, it is coming 14.42 degree. Okay. Now once this is what is known, we can calculate what will be our speed, relative velocity. So relative velocity we are writing in sense of cos component. So cos beta 1, that's what is Ca by V1 based on this velocity triangle. So my V1 is coming 29.25 meter per second. V2, that's what is coming 26.85 meter per second, and de Haulers factor, that's what is coming, it is say 0.92. Okay. Now the next calculation, that's what will be with the degree of reaction. So degree of reaction we are putting in sense of whirl component as well as in terms of my mean peripheral speed. So at mid station, this is what is coming 0.953. Okay. It's a cruel way of doing, because this is what is not a stage. Understand one thing, stage mean I will be having rotor as well as stator. Okay. Here in this case we are having only rotor, but in order to show like whole diffusion or whole pressure rise, that's what we are expecting from the rotor, and as the reason why this degree of reaction number, that's what is coming on a higher side. Now next calculation, that's what will be the consumption of power. So that's what we are writing here in sense of mCp delta T, that m dot or mass flow rate we are writing in terms of density into volumetric flow rate, and this is what is coming 31 watt. If we are considering different losses, bearing losses, mechanical losses, that's what we'll say you need to select this power rating, that's what will be slightly on the higher side. Okay. So you can see we are looking for the design of small fan. That small fan, that's what is required to give small pressure rise. In order to achieve that small pressure rise, this is what is a power, it is reasonable in the range. The next calculation, that's what will be my chord, or what need to be my number of blades. So in order to do that, we will be assuming our aspect ratio. Conventionally for this ventilation fans, the aspect ratio is roughly in the range of 1. Okay, because it is not handling large mass flow rate, and that's the reason why we are looking for aspect ratio in the range of 1. We are also looking in terms of say structural consideration. Okay, so let's assume the aspect ratio to be 1. If we are taking our aspect ratio to be 1, it says my height of the blade, that is coming 0.0625 meter, and the chord of the blade, it is 0.0625 meter. Okay. Now once this is what is known to us, we can do our calculation for the number of blades. Again here in this case, the selection of number of blade, that is always a challenging part. We are designing the ventilation fan at this moment, and for that ventilation fan, the cost will be one of the criteria, and that's the reason why this number of blades selection, that is also very important consideration. So here, in order to have the calculation, we are assuming our mean S by C, mean solidity number, that's what is say S by C as 1.314, and we are calculating our number of blade based on mean radius, that's what is coming as say 7.18. roughly we can say that's what is 7 blades. So for ventilation fans, the number of blades will be in the range of 3, 5, 7, sometimes they are taking or going for 9. Okay, so you can understand this is what we need to put in mind. So here you can assume number of blade to be 5. You can do your calculation for say your pitch, and accordingly you can go ahead. That is also one of the possibility. No one will stop you, but when you are taking these numbers, that time you need to have proper justification. It is not like I will be taking say one number of blade. That's what is next to impossible. Just realize that part. Okay, so understand this are what we are looking for in terms of doing the design. So now we are having number of blades to be 7. Now once we have decided with that, this fan we are talking, that's what is say low pressurized fan, and we are not expecting that to be expensive one, and we are not looking for running that fan at variable speed configuration. Maybe rarely we will be having that kind of, it will be rotating at a constant speed. And that's the reason if you look at carefully, this blade what we are making, that will be made by banding of the plate. So this is what we can say. This is what will be the blade looking like. It is not having aerofoil shape. And as we have discussed earlier, maybe you band the plate, and if it is rotating, that also will be generating the pressure rise. There is a special requirement of aerofoil when we are expecting our pressure rise in a systematic way, because we are having pressure surface and suction surface. We are having flow acceleration and deceleration on my pressure surface as well as on the suction surface, and that's what will be deciding my pressurizing capacity. Here in this case, our pressure rise expected is low, and that's the reason we will be taking band of this plate. Now this banding also, that is important. This curvature here in this case we have taken as a circular camber line. So we will be calculating our Carter slope factor, and this is what is coming 0.274. Once we have calculated that, we can calculate our deviation angle, we can calculate our camber angle and stagger angle. So here in this case, this camber angle is coming 2.73 degree, and the stagger angle, that's what is coming 68.64 degree. Since my delta beta is coming to be slow or lower side, and that's the reason why my camber angle also is not coming on large side. But at the same time, if you look at my blade is too staggered. Let's see what all other dimensions we are getting with. Now once we have done our calculation at the mid station, very next step, that's what will be, we will be assuming our span wise distribution. That's what we have done for almost all designs what we have discussed. So we will not be repeating same thing here. Say for this design, we will be opting with say free vortex concept. Now once we are doing this calculation for ventilation fan, it says the selection of chord, that's what is very important. So conventionally, if you look at your ventilation fans available in at home or maybe at industry or your surrounding, if you look at carefully, my chord near the tip region, that's what is larger compared to hub. Now this is what has to do with the tip clearance, because mainly this tip clearance what we are defining, that's what is in sense of percentage chord. Okay, so that's the reason why this is what is one of the configuration. So for this design, we have taken say linear variation of chord from hub to tip region in a final design. This will give good efficiency as well as peak pressure rise near the stall operation. This also will be helping us in sense of reducing the noise. That's what is of main need. So if you look at carefully, say the fans what we are using for air conditioning system, the fans what we are using for say exhaust, those fans are of special kind and they are having different kind of shape. That's what is being done by using CFD tool. But at this moment we are considering, say we are taking our variation of chord from hub to tip. So here if you look at hub, say at mid station we have done our calculation for the chord, that's what is coming 0.064, and we will be varying linearly from hub to tip. That's what is representing the variation of this chord length from hub to tip region. Okay. Now here in this case, in order to reduce the cost, as we have discussed, number of blade, that's what is very important. Now those number of blades, that's what will be deciding the cost. Okay. So when you are asked to do the design for the ventilation fan, all these criteria need to be considered with, because we are having great competition amongst different distributors, amongst different manufacturers, and that's the reason why when you want to stay in competition, your product need to be of cost effective, and that's where this design, that's what is coming into the picture. Many times cost may not be the only criteria. People, they are talking about having noiseless or energy efficient fan. Under that configuration, you need to go with the efficient design, and that efficient design only you need to do with. Okay. Now once we are going with this, what we know, as per our understanding, if we are opting with the free vortex, we will be selecting Cw into R equal to constant. That's what we are calculating at the mid station. This constant we will be putting from mid section to tip section, from mid section to hub section, and based on that we will be calculating what will be our Cw2, and based on that we will be doing all our calculation as we have done for almost all cases. So once we are doing that calculation, this is what is a final design sheet. You can look at here. In this case, we are doing our Cw into R equal to constant. That constant we are calculating here, and that constant, that's what will be helping us in order to calculate the Cw2 value. Based on that, we can calculate our delta beta. So here, as we have discussed, delta beta, that's what is coming on a lower numbers. So you can see it's a 6 degree, and here almost it's 1 degree. Okay. Now if we look at the degree of reaction, that's what is coming on the higher side. Just understand, do not say like, sir, this is what is not a stage, but we can say we are doing a whole our diffusion using the rotor. So this definition can be applicable for, in order to understand, in order to realize how we are doing our diffusion with rotor. Okay. Now here in this case, my camber angle, that's what is varying all the way from 4 degree to almost 5.66 degree. At the same time, the stagger angle, that's what is coming to be on a large side. So let's look at the blade, how it will be looking like. So this is what is, as we have discussed. So we need to bend our plate. My leading edge and trailing edge, that need to be slightly circular one in order to avoid the flow separation. We know when we are having sharp edge, there are more chances for the flow to get separated. So in order to have smooth entry, we need to give certain amount of radius at the leading edge and trailing edge. Okay. We can say this is what is my blade looking like. Here in this case, my variation of theta, with what we say camber angle, that's what is lower, but at the same time stagger angle, you can see that's what is varying all the way from hub to tip. Now in order to understand how my blade will be looking like near the hub region and near the tip region, so this is what is a rotor we are discussing for this ventilation fan. So this is how my ventilation fan, that's what is been designed with. So in overall, if you look at this whole course, that's what is specifically been designed with configuration that person or say engineer or individual who is working in a different areas where they are looking for different applications. Whatever may be the application, let it be say for application for industry, for say home appliances, maybe for computational tools, or maybe for your say heating, or maybe for cooling purpose. Let it be all purposes. By going through this all lecture series what we are running, you will be able to do design. So first cut design or preliminary design, that's what I'm confident you all will be able to do once you are going through all these lectures. So here we are stopping with week 11. See you in the next lecture. We will be discussing further for what all will be the further discussion in terms of applications of CFD. That's what is the excitement for all of you. Thank you very much.